So hi everyone, my name is Chen. I'm currently a lecturer at University of Sheffield, and today I'm going to talk about mainly two works about how we could utilize multimodal knowledge transfer, mainly powered by large language models to inform some applications in healthcare. I would like to acknowledge that these two works are mainly done at the time at Imperial and Oxford, where I did my PhD and postdoc. Okay, so maybe just give a brief introduction. So my work is mainly focusing on healthcare. So normally, most of the majority works powered by AI usually can fall into the category of single modality. So here is an example, like you give an image or you give an ECG signal, and then you build AI models to do some downstream tasks. Now with AI, we can do lots of different tasks. For example, measurements like segmentation, detection, or some regression. You can also do some diagnosis, which is simply a classification task, or some prognostic tasks, which is basically predicting the risk of feature. Okay. I would like to do a small quiz here, which I did before. So imagine you got some chest pain and you're going to NHS, and then the clinician tell you, okay, we now have an AI tool. Would you like to use? How many of you will like the AI to do the diagnosis? Can you raise your hand if you want? Okay, good. Oh, this is better than last time.
That's why we're here, right?
So we got like 30% of people thinking that, okay, it's okay. So, but we still have like 70% of people don't want to use AI. So there is kind of like a trustworthy issue here, and that's why I'm here. I'm going to talking about some work we could do to better improve the trustworthy AI, so that clinicians and patients are more willing to use it, which will be at probably the end of this talk. Okay, so let me simplify the AI system for healthcare into this paradigm. You got some data, and you got some model. Okay. And then you can do some learning process using some supervised learning by giving ground truth, right? It's very simple. And then you, based on that model, can do some inference. So in healthcare, one of the very challenging issue is that you got very limited data. Why? There is some like labeling costs, because you cannot ask random people to do the annotation right. You need some ethical expert. So it's very expensive to ask them to do the labeling. The second question, second problem is about the label inconsistency. Actually, different countries, different clinicians, they undergo different training programs and at different levels. So they will give you different labels if you ask them to label a large-scale data set. Okay. And the third, but the most important issue is about privacy issue. It's impossible to ask the hospital in all of the world countries and to share that data. There we will have some ethical problems and also some privacy issues. So how can we solve this problem with limited data? So one thing, one way to do that is we're trying to look into some clinical report that is widely available, not only specifically for one of the specific tasks, but it's for general tasks. So normally, for example, for the X-ray, you got some reports and saying that, okay, this is a patient kind of like is normal, and there may be some like degenerative changes in some part of the images. And for the ECG, you also got a report like, okay, this is a normal reason, and then we found some interior reveal. Those reports are widely available in existing data. We do not require the clinicians to do extra manual labeling. So right now we just utilize this medical report to first pre-train a general proposed foundation model. Okay, so here it comes to the solution, right? So we got some external data with some report, and we first pre-train the model. Okay, in that way we're trying to transfer some clinical knowledge into this model, so that and then to utilize this report, you need to have, for example, we have now very powerful large language models. Many of people have already covered that, so I will just skip that. So you can use that to analyze the report and then retrain. So this is the first stage. And then you can fine-tune on a task-specific fine-tuning, which is often the case, very small number of annotated data. Okay? So, here is one of the applications we made. We do some like medical image, or here is the X-ray tasks. There may be 3 different tasks we covered: classification, semantic segmentation, and object detection. So before we're doing the downstream task, we could first utilizing some extra data from public dataset and do some alignment. One of the unique contribution of this work we introduced is that we introduced some orthogonal localization to the latent space of vision. Why we are doing that? The reason that if we purely align the vision concepts to the text report, then there may be some concepts that are missing from the report, right? So you cannot ensure that the basic foundation model really learns some comprehensive features that could be beneficial for the downstream task. So here we're trying to make it the latent features to be independent to each other. If we visualize the latent space of the vision model, you can see that the last column here is our proposed one, and you can find that it actually gives you like expand a larger space of the latent space, which means that it's more informative, and also we're trying to encourage the independent of features, so that is not too much redundancy in the latent space. Okay, this work is very simple, and then we try to evaluate our result. So here, once we got that latent representation of the vision encoder, we fix it, and then we directly fine-tune the downstream decoder. Okay, and we do 3 different tasks, and among all of them, our method performs the best. And especially if you look at the segmentation, which is kind of like a very annotation tedious work if you're trying to ask clinicians to do it. So we're just using like the 1% of the training data, and we got the performance improvement from 0.9 to 52%. So there is a huge jump, right? And this is purely thanks to the large language informed pre-training. Okay. So now I have talked about the first part, which is just give you a paradigm about how we can utilize the medical report to reduce the annotation of downstream tasks. The issue arises also when we are dealing with medical reports, because medical reports can be full of chaos and uncertainty. What does that mean? So one example I want to show you here is about PDB XL, which is the ECG report dataset. When you go through this dataset, you will find that there are mixed languages. So you got a medical report written in German, but also medical report written in English. So how can we let the language model to deal with the concept written in different languages? The second issue about medical report is that pre-assessed medical reports often are uncertain. What does it mean? So here is also another example. So if you look at these sentences, you will find some modal adverbs, like something is most commonly due to, something is likely to be, and this patient may be is likely to have some heart failure or ischemic heart disease. This is because when clinicians are trying to drafting down this report, they're trying to be more conservative because they only get the measurements from ECG purely. Okay, so they may need to do some further imaging, like MRI measurements, to confirm whether this patient really has some certain disease. So how can we let the language models to deal with this uncertain information? Okay, so we propose a very simple approach, which is trying to convert this raw text into some clinical defined SAP codes. So here we're trying to just, even this are writing in different languages, but we can convert them into the same SAP code. For example, this one, you know, this is a kind of like a normal ECG. You can look at the one highlighted in green region. Okay, and on the right-hand side is the report writing in English, but both of them we can convert them into the same set of SAP codes. Okay, and you may notice that there are also some numbers associated with each SAP code, which represents the confidence of these statements when the clinicians are writing down this report. So, for example, here they saying that the findings are likely to be due to some disease, and then we got a likelihood which is 50. So now we got, for each ECG, we got a set of SAP codes together with these confidence scores. Now the second question is, how could we leverage the language models to deal with that specific format of data? So what we do is we trying to looking into the knowledge base of the clinical sites. So for the SAP, they have a kind of like a knowledge base which represented SAP codes and described it into the category and also its specific descriptions. So we can then utilize that to generate some statements about each SAP code. So then after that, we can get specific representations for each SAP code. So in order to leverage the confidence score, which I can just do some average weighting based on the confidence score, and then we can get a representation for each different ECG report. So it's very straightforward, right? Okay. So here I'm going to present one of the applications based on this paradigm. So we first pre-trained on our kind of like a deep learning model on this PDB Excel public data set with report. And here we do some alignment. And then we fine-tune these models on UK Biobank, which is kind of like so far one of the largest longitudinal study in the world. One of the issues with the downstream task on the UK Biobank is that there is only a very small portion of future event data. So here is an example, right? We look into two cohorts. One is those patients had some hypertension events in the past. The other is has some like myocardial infarction event in the past, which they may develop heart failure in the future. So we look into their ECG at some time point, and then also look at the future event data. So because UK Biobank is kind of like over healthy population. So we found that in the end, there is only a very small portion of these heart failure events, which indicates the risk of getting overfitting. So now with these large language models, specifically with structured report, we found that our performance looks even better than those just purely trained from scratch. And if you look at this second cohort, which is a smaller cohort, the performance improves from 0.5, which is basically a performance of random gas, to 0.58. So the measurement here is the same index. Normally, clinically, the value should be range from like 0.6 to 0.8. Okay. We also compared to our very strong baseline. It's just using ChatGPT and other translation models to translate this report into English. Okay. And this is on the last second row, and you can see that our method performs better, which indicates the benefit of incorporating uncertainty information and to unify them into a set of SAP codes. Okay, so here is a visualization of the latent space using SAP codes to extract some representations from AIM. If you color them according to their super class, you will find that the AIM successfully encode them based on their clinical meanings. And one potential finding you may find is that there are some brain clusters are far away from those pathological clusters. So here the myocardial infarction is kind of like a very pathological variations, and the top up cluster, which are blue, which means that they have abnormal SDMT changes. These actually can be healthy variations found in healthy adults. So it's kind of like suggests that the LLM can really learn some representations based on these SAP codes. Okay. So another thing, I promised you that I will show you some technique we're trying to improve the trustworthiness of AI, right? So here, the underlying transformer or encoder we're trying to make is using some visualization. So when clinicians are trying to, using our AI models, we want to let them know where AI is looking at when they're making this decision, right? Although you have a very powerful models, but what about its performance on a specific input, which is the one that the clinician is really caring about. So we built a specific ECG transformers which trying to visualizing the analyzing or to understand the cross-lead interpolations. So clinically you have like 12-lead ECG signals, and also trying to visualize the temporal changes of this ECG code. It's basically trying to looking at the ECG both at global view as well as the local views. Okay. So now here is kind of one of the examples. So we found highlighted regions are those that the deep learning model really pay attention to when they're making a decision about whether this is a high risk patient or not. And it's very interesting found that you can see that most of the R peaks, which is basically the highest peak here, the AI models can successfully recognize it, although we didn't teach the AI models to do that. And even there are some noises in lead 2 you will find, it can still recognizing this R peak. So it confirms that the network actually performs robust even when there is a noise presented. Now, if you look at the cross view, which is global view, there are also very interesting findings. So the leader 2, which is highlighted here because it has significant noise, right? So this suggests that AI model know that this leader 2 is very significantly different from the other ones, which are kind of like clean data. And if you look at the right bottom here, you can see a good diagonal regions are highlighted, which means that there has a good synergy between V1 and V6, which indicates a good R wave progression. So this is all consistent with clinical knowledge. Okay, so we also did some comparison study using different networks, and our networks being both lightweight, also explainable, outperform the other existing SOTA network architecture. Okay. So here comes the conclusion. So I talk about how we could utilize multimodal informed pre-training to reduce the dependency of annotated data, right? And it can helps to elevate this overfitting problem. I also talk about that when we're dealing with medical report, it can be quite chaotic and can be quite full of those uncertainty informations. Then we present our work trying to restructure and trying to incorporate this uncertain information into the representation learning. And finally is we're trying to highlight that actually both network architecture as well as the structured LLM trainings are both important to contribute to the trustworthy machine learning for healthcare. So that's briefly my presentation. And you can scan my QR code to get my linking to get connected or follow my Twitter. So any other questions?
Is there any way to automate the process to get the SCP codes from the reports?
So currently, we directly working with the public data, which are already done by clinicians with human verifications, because the uncertainty information is provided by the clinicians rather than automatically done. But I'm sure with you can prompt the ChatGPT, for example, to extract those entities and those verbs that corresponding to probability to automate and to make it fully automatic. Yeah.
I think the signal data nowadays, for example, we are wearing the smartwatch, right? So there are some PPG signal as well. So I think you mentioned about the noises in the ECG data. Yeah. So how hard it is to cultivate the model training for such a noisy thing in the ECG data.
So I guess this is a good question. So in our case, we're working with 12 leads. So certain amount of uncertainty can be, or the noise can be reduced because there are other different leads to inform the decision. But if you're working purely with single lead, for example, the wearables, you may get only one single lead ECG, then it may be better to do some data augmentations to get move that. We have lots of adversarial data augmentation and random augmentation for that part. But we didn't have it for the signals. One thing that the signals are really difficult to do augmentation. If you do small changes, it might affect the T wave, which is a small part of the signal, and then it will totally modify the class labels. So here, that's why we're trying to directly using large language model and report to do that rather than data augmentation. But there are some works that do some random masking or adding some Gaussian noise, but which is very mild noises to do this. Yeah.
Thank you. A following question is, so I think the signal data is time series, right? So in terms of the data you use, are they the fixed time point, like 60 seconds or 1 hour ECG?
That's a very good question. So we actually do some pre-processing. We are working with the median waves, which is kind of like average of these time series. And the median wave can be directly obtained using current ECG device like GE. They provide the median wave, or you can use some AI algorithm to get it. So we tried with long time series with different lenses because we are working with transformers, so it should be adaptable to different lenses. But we found that in terms of the robustness, median signals works better than the original row time series. Thank you.
Okay. That's Chen.